Okay, example 2 on 4.6. Given a function f of x is x times the square root of 5 minus x, find all intercepts, extreme points, inflection points, intervals of increase and or decrease, intervals of concavity, and asymptotes it might have. Use this information along with any extra points you feel necessary to include to graph the function. So, basically, graph the function as accurately as possible with as little information as possible. Okay? It seems like a lot of information, but again, to get a really decent graph without knowing anything, you'd have to pick thousands of points to find specific numbers. I want to find maximums, minimums, inflection points. Those three definitely need to be there. Calculus is going to pinpoint those for me. And then once you've gotten those specific points, then the randomness of picking happens, and you can get as many points as you want to create this graph. So our function f of x equals x squared root of 5 minus x. First thing I want you to get across to you before anything else, I could have taught my Algebra 1 class to graph this. Pick x, solve for y, plot the points, connect the dots. Okay, back when we graphed lines, we picked x, we solved for y, plotted the points, connect the dots, right? And there were lines. These are curves, so they're a little bit more complicated than lines, but the idea of picking x, solving for y is still there. And your calculator is going to be doing the solving for y for you. So know that anytime you want to point on your curve, it comes specifically from that equation. Okay. Keep it as basic as that for the most part. Okay. I know calculus is much more complicated than that typically, but that's the basics of the problem. Anything you want to pick, if I want to pick 17 for x, well, I can't because square root of negative 12 is undefined. But if I want to pick 2 for x, I could. If I want to pick 1.9 for x, I'm allowed. 4.77, I sure could. Okay. Are those going to be specific points that are really important and necessary that find me specific numbers or specific points? I don't know. But I do know they all lie on this curve. All right, so know that anytime you need to find a dot that goes on the actual picture, it comes right from there. All right, what calculus does is it uses the first and second derivative in order to find more important stuff. So if I go to my first derivative, f prime of x, keeping in mind f of x is that, and the structure I would use for differentiation would be x parentheses 5 minus x to the half power, right? And I got to differentiate using my differentiation techniques we learned back in first semester, and that is, in this case, the product rule because it's a product of functions. And within the product rule, when I differentiate function 2, that's a chain rule going on there. So, if I'm differentiating by the product rule, function 1, function 2, if I go 1d2, it's going to be x times 1/2 times 5 minus x to the negative half times negative 1. The structure of function 2 there is a product function, so I use the product rule, I'm sorry, the power function, so I use the power rule. So the power 1/2 times the base 5 minus x to 1 lesser power, 1/2 minus 1 is negative half. Then I got to multiply by the derivative of 5 minus x, which is negative 1. Okay. Then when I do 2d1, it's going to be 5 minus x to the half times 1. For this specific structure of problem, that's the right answer. Okay, but I want you to have some simplification techniques understood, bless you, expected on these also. So, first off, negative times x goes on top, and 2 times the square root of 5 minus x goes on the bottom. The second one, I've got the square root of 5 minus x on top. All right. What I want to get across to you here is when you have this structure to begin with, something times a radical, you're going to get a derivative looking a lot like this. That's not wrong, but it's not as easy to get what we need out of that as we would like. So what I want to convince you of here is I want to get a common denominator to add the fraction to create one simple fraction out of this whole thing. In this case, multiplying top and bottom of this by 2 times the square root of 5 minus x is going to accomplish that. So if I continue to simplify this, f prime of x equals, I'm going to get negative x over 2 times the square root of 5 minus x. And then on top, I'm going to get 2 times 5 minus x over 2 times the square root of 5 minus x. Just creating a basic common denominator there. Square root of 5 minus x times itself on top here just creates a 5 minus x with no radical times the 2. And all of a sudden, I got f prime of x equals, if I distribute this and combine like terms, 2 times 5 is 10. 2 times negative x is negative 2x, plus the negative 1x here makes a total of negative 3x, all over 2 times the square root of 5 minus x. Okay. For me personally, all this stuff here, up here, is a scratch sheet of paper. This is what I want to have in my work. These problems have plenty of work to be shown. Okay. This is all good stuff, but it tends to take up a lot of space. And all of a sudden people are trying to cram more important stuff into a little tiny space because they run out of space. Scratch sheet of paper here, this is what goes in the paper. So we just take all of that. There's my scratch sheet of paper over there. And there's, oops, there's my important stuff. There's my f prime. All right. What I'm going to do with the derivative here is I'm going to find critical numbers of the derivative. Critical numbers occur at endpoints, which there aren't any. They occur when the top of the fraction equals 0 or when the bottom of the fraction equals 0. Okay, so when you're dealing with a rational structure, which again, when you start off here, it's not rational, but when you do a derivative, you're going to create a rational structure, stuff over stuff. So no endpoints, top equals 0. Determines when the fraction equals 0. That's that equals 0 criteria. Bottom equals 0 meets the criteria of undefined. If a rational function divides by 0, you got an undefined situation. So this to solve it, I'm going to move the 3x over to the right, divide by 3, I get 3.33. 10/3 is exactly right, but we're graphing, so a couple decimal places is perfectly sufficient on these. 3.33 is a critical number. Over here, if I square both sides, I'm going to get 4 times 5 minus x is equal to 0, which is just as good as saying 5 minus x is equal to 0. 5 minus x to be 5 minus x equals 0. Notice this is already in factored form, right? Can 4 equal 0? No. 5 minus x can though, right? So the 4 doesn't really matter there. So this gives me 5 equals x. Okay. 5 is undefined. That's where it's undefined. Okay. 3.33 is where it equals 0. So both of those are critical numbers. One other thing I might have noticed before I even started this, and I kind of already did, but just to remind you, is that there's an endpoint at 5. If x is bigger than 5, 5 minus bigger than 5 is negative, square root of negative is undefined. We only graph real numbers. So we know that all the answers between negative infinity and 5. So there's not an interval given to us, but there's an interval we can establish. We can see that 5 is the endpoint. 5 is also the critical number. It works itself out anyway, even if we didn't notice that to begin with. But just know that that's what's going on here. So as far as my setting my intervals up, I'm going to go all the way from negative infinity up to 5. So from negative infinity to 3.33, and from 3.33 to 5, something's going to happen in this graph. Suppose the left-hand work here, suppose this says x equals 6. Okay, 6 doesn't fit in there, right? So just throw it out. So that happens occasionally too, where you get a number that's a critical number, but it's outside the interval you're working with, then it just doesn't matter. All we care about is what we're allowed to graph. So, negative infinity to 3.33, 3.33 to 5. If I pick a test point here, I'll go 0, and test point there 4, and we're evaluating this function here. 5 minus 0 is 5, square root of 5 is positive, times 2 is positive, right? All we care about is positive or negative, we don't care about numbers. 10 minus 0 is 10 positive, positive over positive gives me a positive. If I try x equals 4 in this function, 5 minus 4 is 1, square root of 1 is 1, times 2 is positive 2. On top, 10 minus 12 is negative. Negative over positive makes a negative. So I can see right off the bat, just for my first derivative, I can see it's increasing all the way to 3.33. Then it starts decreasing until it gets to 5, and then it stops. And if it increases, then decreases, it's going to hit a maximum value at the critical number. That's everything I can do with the first derivative. Okay, find the first derivative, find your critical numbers, create your intervals, test the intervals, and establish increasing, decreasing, and of course, max and min. Once you've done all that stuff, now we move on to the second derivative. Second derivative, notice the function itself is a quotient, so I have to use a quotient rule to differentiate. Low d high minus high d low over the square of what's below. So if I do low, that's 2 times 5 minus x to the half. D high is going to be negative 3. Nothing weird about that, right? I used the half power structure instead of the radical structure, but d high was easy. It's just a polynomial. Minus high d low is going to be minus the top, minus 10 minus 3x. D low, all right, so if we take a look at the low, 2 times 5 minus x to the half, right? If I differentiate that, 1 half times 2 is 1. 5 minus x is 2, we need negative half times negative 1. All right, so altogether I'm going to get, I'll just go 5 minus x to the negative half times negative 1. Over the square of what's below, if I square that, I'm going to get 4 times 5 minus x. Again, doing whatever's possible to make it as pretty as I possibly can. Again, this is scratch paper work. This is not what I want to have on my actual work that I'm doing on my paper, on my homework, but I'm doing this on a scratch sheet of paper until I get this nice looking thing like this, as simple as possible. So, if I go ahead and simplify this now, once I've differentiated, once I've gotten the derivative taken care of, now I want to go back to radical form instead of half power form. So I'm going to get negative 6 times the square root of 5 minus x. Really am having trouble writing minus x today. There we go. All right. This minus and this minus together make a plus plus here. So this goes on top, that goes on, that should be negative half here in case you don't have that in your work. Just notice I didn't have it in mind. Negative half. So this goes on top, this goes on bottom. So plus, because again the minus minus made a plus, 10 minus 3x over the square root of 5 minus x, all over 4 times 5 minus x. Once again, we start off with the structure we have there. Something, square root of something. Okay? You should expect a second derivative to look a lot like this. Okay, your first derivative is going to look a lot like this, probably have a radical in the denominator. That's going to create one of these fractions within a fraction situation with a radical involved. I'm going to multiply top and bottom by the square root of 5 minus x to get rid of this fraction. So this entire thing times the square root of 5 minus x. And this also multiplied by the square root of 5 minus x, but I'm going to write this in that manner because I'm multiplying the same base with powers. It's easier to add powers than it is to deal with an extra radical there. So if I go ahead and do that, I have to double prime. When I do this times this, the square roots of 5 minus x multiplied by 5 minus x without a radical times negative 6. When I do this times this, the square roots of 5 minus x cancel, leaving me with plus 10 minus 3x. All that goes over 4 times 5 minus x to the 3/2 power. And then all this left to do is just combine like terms after distributing. So f double prime of x equals. All right, so we're going to get negative 30 plus 10 is negative 20. Positive 6x minus 3x is going to be plus 3x. All that goes over 4 times 5 minus x to the 3/2 power. And just like that, we have our second derivative, as simple as we possibly can. Throw my scratch work back on the scratch paper. Okay, so there's my second derivative. Now I need to do all the same stuff with my second derivative that I just did with the first derivative. Find my critical numbers. If I start, the top could equal 0, or the bottom can equal 0. So the left-hand one here, negative 20 plus 3x equals 0, that means that 3x equals 20, which means x is equal to 6.66. What do you think about that one? Actually, 6.67, actually, if I round. Got it round properly, 6.67. What do we think? Anything wrong with that? Nothing at all?
I don't think so. I can't because it's bigger than 5. Oh, yeah.
Remember, we have a specified interval here because, again, based on the rules of square roots, we can't have the square root of a negative number. 6.67 creates a negative number, so even though it's a critical number, it doesn't work because it's outside the interval that we're going to be dealing with. All right. Here, I can square everything to get rid of the half power, but notice it's already factored. This times this equals 0. If 5 minus x equals 0, then x is going to, then this whole thing's going to equal 0, right? So that gets me x equals 5 for a critical number there. So all this tells me is the concavity doesn't switch all the way through. It's going to be something concave up or concave down. If I go from negative infinity up to 5, pick any test point I want. Let's go with 0. 0 is easy. Put 0 in here. I'm going to get negative 20 plus 3 on top, or sorry, plus 0 on top, which is going to be negative. If I put 0 in here, I'm going to get 4 times 5 to the 3 halves power, which equals some positive number. Negative over positive equals negative, so it's always concave down. No inflection point. So, a lot of work. I found exactly one point. It's a maximum. I know about increasing and decreasing. I know it increases, hits a maximum, and decreases. I know it's concave down always. So everything that I figured out now is legit. Now it's just a matter of graphing this on graph paper. But I want more than one point. So let's just take a look at what I have so far. I know I have an endpoint. You always want to pick an endpoint. All right, so always pick that. 3.33 is a max, and that's all I have for information. I'm ready to actually evaluate this thing, so I'm going to go here, type in x square root of 5 minus x. Okay, again, anytime you're starting to fill out this chart, I want you to equate this chart with f of x. Never ever use this chart here with any function other than f of x. I've seen people too often put f prime and f double prime into that chart. And I say this every year, when you start filling in this chart, we're going right here to f of x every time. The calculus found me all the x values I need to use, so I go to my table and type in those, 3.33. Try again here. So 3.33 and 5. 4.30 and 0. Okay. Again, I know that 4.30 is the absolute maximum, right? So I just kind of want to get a feel for now how deep, how low does this thing go. All right. What other numbers do you think we should pick?
4.
And?
2.
Keep going.
3. 1. 0.
And so on, right? The extra points you pick is just going to give you more clarity as far as what the graph's going to be. All right? There's no magic to those numbers. We're just going to pick randomness. So again, going back to our Algebra 1 days, here graph this line. When we first learned to graph lines, we picked x, we solved y, right? Once you've used your calculus to find everything you can about specifically special points, every other point's just going to give you clarity as far as what the graph looks like. With lines, we needed 2 points. With curves, sometimes we need up to 10, 15, 20 points. We don't know what the curve looks like without getting enough points on there to look at it. So pick some values. Your calculator's going to evaluate them for you. The difficulty here is just how much do you feel like pushing numbers. Okay? None of these numbers is ridiculously out of the ballpark, right? I mean, if I got -1 comma negative 15,000, I don't want to graph that point, so just leave it off. But all these seem reasonable. So 4, 4, 2, 3.46, 3, 4.24, 1, 2, 0, 0, negative 1, negative 2.45, negative 2, negative 5.29. Notice the importance column is being left empty there because those aren't important. They're not maximums, they're not minimums, they're not inflection points. They're just extra points in the curve that help give us a clearer picture of what the curve is supposed to look like. And then we go on to get some graph paper. Maybe. The points I need to graph are all the way from negative 2 up to 5, and go up to 4.3 or go down to negative 5.29. So I would probably put my x-axis here kind of in the middle, and I'd want my y-axis maybe off to the left a little bit more to give myself more room over to the right. I got to go further over there. Here's x, here's y. So 1, 2, 3 and a third. 1, 2, 3, 4.3. So about here is the maximum. 5, 0. We got 4, 4. We've got 2, 3.46. We've got 3, 4.24. We've got 1, 2. We've got 0, 0. That doesn't seem right. Oh. 3.46 might help if I actually go up the right number. Counting 1, 2, 3.46. Okay. 0, 0's here, and then negative 1, 1, 2.45. Negative 2, 1, 2, 3, 4, 5.29. Okay. Notice how it looks. It looks like it's going to come up, hit the max, start turning back down. It looks concave down all the way through. Everything that my calculus told me was supposed to happen is happening here. Notice this is a closed circle endpoint because, again, 5 is allowed to be a number on this graph. There's no undefined value to it. So I just draw the graph concave down. Make sure I go through the maximum and then stop there. Arrow on this side, endpoint on that side. For verification purposes, if I wanted to graph this with my calculator, I should see very much the same picture. I want to get my scale similar to what I have here. So if I go from negative 1, 2, 3 up to, let's go 8. One scale on the x-axis and go from negative 6 up to 5 with a one scale on the y-axis. Hit graph. You should be looking at pretty much the same picture. It kind of missed this by just a smidge because, again, the way your calculator thinks is it picks numbers and plots them, right? It didn't pick 5 exactly, but it picked 4.9972 maybe. And then the next number I would pick would be 5.0182 or something like that, which is undefined, so it stops where the last number it got was. But again, what you see on your screen should resemble what you have on your paper. When you plot this, what I'm looking for as far as grading these things, I'm looking for all the numbers that you have to have. Whatever extra points you pick should be correct. Okay, if you don't pick the same extra points I picked, who cares? As long as they're on the correct graph, I don't care. I should see the graph drawn correctly, and if you miss a point, something like that, I'm not going to account off for that, but just kind of try and make the line connect on the dots. But you know, if you're off by a little bit because of estimation reasons, or maybe you just had trouble making the graph hit that when you're drawing it, I'm not going to count off for that. I'm looking to see if you use the calculus correctly, that you did all this stuff correct. I'm going to assume if you have the correct derivatives that you somewhere on a scratch sheet of paper did all the correct work. All right? Looking to see that this is correct and the rest of the points are all accurate points. And that your graph looks pretty much like it's supposed to look. Identifying important points on the graph. You don't have to write end point, I can see that. Max, min, inflection point, end point.